Hi everyone, I'm Michael. I guess I should have the microphone. I would like to congratulate everyone. This is the last 15-minute talk of the conference, so everyone should be happy. So, as I'm sure everyone is aware, the Earth has a magnetic field. But the problem that we have, we can measure it quite well now, but measuring it in the past is a bit more difficult. So one of the ways that we can connect what we can see now to how it used to be is by looking at lavas, because lavas record the magnetic field when they form. So in this case, we had a nice little lava flow in the 1960s, in 1960 in fact, from the Kilauea volcano in Hawaii. And so at this time, the Honolulu Observatory, which is a couple islands over, recorded a 36.5 microtesla field strength. That's pretty standard for what you'd find on Earth. Usually it's around the 50 microtesla is about as high as you'll find it. Am I too loud? And so in order to do this, we get samples of the actual lava. This is me over at one of the areas of the lava flow. However, this trip had absolutely nothing to do with the sampling. I was just nearby it about 55 years later, so it was quite a while later. This actual sampling happened in 1999. But first, we have some background to paleointensity, which is how we actually determine how strong the magnetic field was. Because I know we only have about 3 paleomagnetists in here except for me. So first, this is the magnetic field of the specimen. They'll be blue. And this will be the field that we apply to the specimen. It'll be red from here on out. So first we need to demagnetize it, because we have some magnetic field, and so we need to now change its magnetic field. So the main way that we need to do this is the field loses strength as temperature increases, and we can also do the same process using microwave radiation. Basically works the same way that an oven versus a microwave oven works, just at different frequencies. So we take the specimen's magnetic field, we add some radiation, whether it's infrared or microwave, and then the magnetic field strength decreases. So we then measure this change in the vector, and it gets smaller. So that change is something that we record. Now there's a couple different ways to remagnetize it. So the first way is to do it perpendicularly. So we start with the sample's magnetic field, and we orient it straight up in the z direction, or the z direction if you prefer. And then we heat the sample up while applying a field to it. And because one gets shorter, the magnetic field gets shorter, and we apply field, so we get a new field. And that new field is what we want. And we repeat this method continuously. As we change the field, we measure how the changes occur. And those changes are what actually end up telling us how strong the Earth's field was. So now, there's another method called ISI. The reasons for it being called ISI are unimportant, but the takeaway, it does the demagnetization and the remagnetization separately. So it effectively requires 2 equations, both of them in 3 dimensions. So we take the specimen's magnetic field, we then heat it up, and we then get a smaller field, and we measure how that changed. We then take that field, we then apply the new field to it, we add some radiation, and we get a new field. Nominally, this purple line should be the same as the purple line that you saw before. Whether it is, that's the fun of this project. So then we have PTRM checks. These are a fancy term for, can we reproduce what we just did? And this is the best way to check for thermochemical alteration. Because it turns out, when you heat up a rock, it tends to oxidize. And that's bad when we're working with iron oxides, which is what you tend to find as magnetic carriers. Because if the sample alters, we can't use it because we don't know how its magnetic properties have changed. So now let's come back to Hawaii and the 1960 work. There have been 11 previous studies on this lava flow, and they've pulled out something between 31 and 56 microtesla. The goal was 36.5. This is quite the range. So 18 years ago, when I was the very old age of 5, there was a study from the University of Liverpool on 70 specimens using the perpendicular method, the one that uses demagnetization and remagnetization at the same time. They sampled 2 sections from the lava flow, and they pulled out estimates of 31.3, the lower bound, and 37.1. 37.1 is not so bad. 31.3 is a bit low. And if you weight them based on which come from which section, you pull out about 34. It's okay. We can do better. New work. So came back to this. We want to figure out why the 31 is so low and why that section is different from the other section. So this is where I come in. I ran 105 specimens. I managed to pull out 69 new estimates. So we had a pass rate of about 2/3. Not bad. Sometimes you can get pass rates down to about 1/3. So these rocks are working okay. I had to use 3 different methods, though, in order to get this to work correctly. Perpendicular, which is what was done before, so I can check my work. I added PTRM checks to the perpendicular, so that not only can I check my work against what was done before, but I can check my work against myself. And then ISI, which always has PTRM checks in the way that we do it. And this is the new modern method compared to the older 2 methods. So if the literature is to be believed, this one should work correctly. So we now pull up these fun plots that are known as Arai plots. And the takeaway from these, the important part, is that in a perfect world, we would have the data go from 1 to 1. And each one of these is a different heating step. And they should line up really nicely like this one. But they tend not to. So with these, we were hoping to pull out something around 36. And we see with the perpendicular method, we pull out numbers that tend to be too low, even for ones that are very linear, which is the same behavior that was seen in the previous paper. If we add in the PTRM checks, so that we can actually check our work to see if there's been any alteration, we do a bit better. We go up to 33 compared to 30. These 2 are sister specimens, as are these 2. But it's not perfect, because this one was at 35, this one was at 34.2. So they are quite close, but the problem with that is that even though they're close, it's still not quite right. But we're getting there. So if we look back to what they did before, we actually see that our perpendicular data lines up incredibly closely with theirs for section 1, and pretty close for section 2. If we throw in PTRM checks, however, we get a roughly 5% increase in the estimate of the magnetic field at the time. So this additional estimate gets us closer in both cases to what we would expect it to be at about 36. So now we move on to the modern method, which we hope should give us the most correct answer. It's a bit high. So we see here that we get 39.6 and 38.4 for section 1. We have some nice straight lines, but then we also have this zigzag right here. So that zigzag is why we use ISI now. If there's a zigzag, that means we have magnetic grains that violate Thellier's laws. Thellier's laws are the laws that govern paleomag. And the shortened version of the laws are, we should have a nice 1-to-1 line that goes from there to there. That's the important part of the laws that everyone should know. And this zigzag means we're violating them. Oops. So then we move on with section 2, and we see similar behavior with the zigzags, which means further violation. So now, if we look at this and we average them all together, we start with the very low estimates, we replicate them, we get a bit higher, and then with the ISI data, we get really close for section 1, but with section 2, we're too high. So section 2 has more of the zigzag behavior to it that's causing these estimates to be too high. So we get this 8% increase here. So now the question is, can we do this in reverse? So since we separated the DMAG and the remag, can we pretend like we didn't? And so analyze the data together. Turns out we can. So we take this ISI plot, pretend that we did everything at the same time, replot it, and the estimate drops. We repeat the process, take this ISI data, pretend we did everything at the same time, the estimate drops. Notice how for this one, these 5 data points weren't selected. This black line became this black line. So that means that whereas for these we didn't select them because the PTRM checks fail, because this black line shows that we don't want them, and they're zigzagging, we get a lower estimate. So we can do it in reverse. We can pull out these lower estimates. So if we look at the retreated, fake data, we see that we can take the higher estimates, drop them, and then take them back up. So we can drop them to the low levels that we see from the old data, and then pull them back up slightly. So we know that alterations are occurring because we can't see them with without the PTRM checks. We have the non-ideal grains because we see the zigzagging. Perpendicular can't detect them because of the lack of zigzagging. So overall, we're going to need a multi-method approach because otherwise we just can't find the problems because we got the overestimates with ISI from the zigzagging, and we get underestimates from perpendicular without the zigzagging. Thank you.